So what are the quantities? Almost all gas properties are determined by four interrelated quantities. The pressure of the gas, the pressure due to the beating of the molecules against the surface, against really anything that is in that gas, our bodies, the chair, whatever. The temperature due to the kinetic motion of the gases, so the kinetic energy of the gases, higher temperatures, there's higher kinetic energy in the gases, and so they pound against the walls more vigorously. The volume amount of gas is contained in, and the number of molecules in that gas. So pressure depends on, as I've been saying, the frequency of the collision with the walls. It depends both on the number of molecules. If there's more molecules, it's going to hit the walls more, the pressure will be higher, and also the volume. The smaller the volume, with everything else being held constant, then the collisions will be more frequent because the same number of molecules are rattling around in less volume. But also depends on the speed, the kinetic energy of the molecules. The faster the molecules are, the harder they are hitting against the wall. So those are the properties that we'll be looking at. It's important to think about the difference between extensive and intensive quantities, because the gas law is a relationship between both extensive and intensive quantities. So extensive quantities scale proportional to the system size. If you put two of the systems together, these quantities double. The mass doubles. If you put two of the same quantity, two of the same systems next to each other, they will have twice the mass. They'll also have twice the volume if they're identical systems, or also twice the total energy. Intensive quantities are independent of system size. If you put two of the same system together, these quantities don't change. Temperature. If I put two systems that are at room temperature together, then they're going to stay at room temperature. They're not going to be double the temperature. So that's an intensive quantity. Energy per mole. If I put two systems together, their average energy, their energy per mole of molecules, is not affected by whether I put them together or not. So those are intensive quantities. So the gas law relates several intensive and several extensive quantities. You know, the book talks a little about several simple gas laws, and it's good just to think about those to get a sense of, how hot air balloons work. But for the purpose of, and they all relate different of these extensive and intensive variables. So constant temperature and pressure, let's look at Boyle's law, constant T and N, then pressure is inversely proportional to volume. Charles' law, constant pressure and N, volume is proportional to temperature. Constant P and N, volume, Avogadro's law, constant P and N, then the volume is proportional to the number of molecules. One thing, additional law that's sometimes included is Dalton's law, which is basically when you change the identity of gas molecules, the pressure stays exactly the same. If the same number of molecules keep temperature and pressure the same, it's not going to change. If it's an ideal gas, you won't notice the difference if you just look at P, V, N, and T. Okay. So the ideal gas law unites all of these. PV equals nRT, where R is a constant that is of the units of energy over moles Kelvin. We sometimes write it as liter atmospheres, but liter atmospheres, if you remember back from the second day or so of class, is actually a unit of energy. So 0.08206 liter atmospheres per mole Kelvin, or 8.314 joules per mole Kelvin, and this you won't have to memorize, you'll have this that you can look up. Okay, so the ideal gas law is exact for non-interacting point particles, i.e. ideal gas particles. Are molecules non-interacting and point particles, i.e. they take up no volume? Well, for gases at room temperature, it's actually a pretty good approximation. It works best when real gases are moved like ideal gases. Dilute, there's not very large molecular volume compared to the volume of the container. But for gases, at room temperature and pressure, for things like oxygen and nitrogen, it's pretty well satisfied, and at high temperature. But what do we mean at high temperature? Well, any temperature that's well above the boiling point. And so it turns out that for a lot of the things that we see here, gases, room temperature is actually pretty high temperature. For oxygen and nitrogen, it's high temperature. And so this approximation is very good, really within 1% at room temperature and pressure. It's a pretty good approximation, and so we use it a lot. I actually remember a lunch I was having with two chemical engineering colleagues, and I walked through a parking lot and I saw a license plate that said PV, NRT, and I thought that was amusing. I mentioned this to the people at lunch, and one person said, well, you can tell they're not really a chemical engineer because they know that the ideal gas law is only an approximation, and you have to take into more factors into account. And we all said, oh. And he walked off. He finished his lunch, and one of the other chemical engineers leaned over and said, actually, I don't think in my research, I've never used anything other than PV equals NRT, because he always worked in regimes where it was a valid approximation. So is it good enough? Usually it is. And we'll learn about some cases where it's not quite good enough. And later on, if you're doing some chemical engineering classes, you'll deal with cases where supercritical fluids, where definitely PV equals NRT is not good enough. But room temperature pressure, it is. So it's also called the ideal gas equation of state. Any function that if you give it a volume, it tells you the relationship between pressure and volume, that's called an equation of state. So this is the ideal gas equation of state that gives you the relationship between volume and pressure. Given N and T, and you're always given R since it's a constant, it'll tell you how pressure and volume relate. So really, the important thing is you don't have to memorize all those other laws. I'm not going to ask you, can you tell the difference between Charles' law and Boyle's law? Because when it comes down to it, those are just names for things. The important thing is the mathematical relationship. There's one equation that covers all the changes. So if we take a PV and NRT, and a constant N and T, well, let's rearrange it so that we divide by the volume on both sides. And so now we've got P equals NRT divided by V. Well, if R is always a constant, if N and T's are constant, that just says the pressure is inversely proportional to volume. So we got that. So that's Boyle's law. NRT at constant P and N, well, we rearrange it. So we divide by P, and then we get the volume equals NRT. Again, if P is constant and N is constant, R is always a constant, that just says V is proportional to temperature. We keep pressure, number of molecules the same. The volume is linearly proportional to temperature. We double temperature, we double the volume. That's Charles' law. PV equals NRT, well, constant P and T, then if we divide by P again, then if P is constant and T is constant, then the only thing that changes is N. The volume is proportional to N. That's Avogadro's law. And PV equals NRT. If the type of molecule changes, and that's all that, we just changed the type of molecule, then N hasn't changed. We still got the same number of molecules. So therefore, PV equals NRT predicts no change. So it's one equation that contains all those equations. And that's what I'm interested in is, do you know this? So you could, look at solve a problem with Boyle's law, but you could just use the ideal gas law and that'll give you the same answer because it contains all that information. So yeah, that's Dalton's law. So really it's one equation to rule them all and mathematically bind them.